Chapter 2, Section 2, Basic Differentiation Rules and Rates of Change. I believe that after doing the assignment from Section 2.1 that you're going to probably appreciate this section just that much more, because it's going to show you different rules and for differentiation that are going to streamline your work. You're not going to have to be basing it on the definition of the limit as delta x goes to 0 of the difference quotient expression. Alright, so what we're going to do is we're going to start off with some rules that are very basic. Now these rules are proven using definition, but we don't have to prove it. As I've mentioned in a previous video, we stand on the shoulders of giants so that we can see ahead and base our work using all their hard work from before. So we'll start off with the constant rule. Now think about the constant. A constant function is like y equals 5. So it's a horizontal line. And if we try to find the derivative of a constant function, it's as if we're trying to find the slope of a tangent line to a horizontal line. Well, it would be horizontal and the slope would be 0. So the derivative of a constant function is 0. Okay, so that's easy. So we're taking the derivative of 5, we get 0. If we take the derivative of 10, we get 0. So that makes that nice. Easy to remember. So the derivative of a constant is equal to 0. Now the power rule is extremely important, not only in this section, but in some of the other sections that are coming up, and we'll generalize this a little bit later on. But it says here that if n is a rational number, so it could be a positive number, it could be a negative number, it could be a fraction, just couldn't be an irrational number. The function f of x equals x to the nth power, so we're taking x raised to a rational exponent, is differentiable, and the derivative of x to the n is n times x to the n minus 1. Now I kind of think of that as whatever the exponent is coming out in front and then just taking 1 off the exponent. So n times x to the n minus 1. Again, this is pretty useful also because we have so many polynomial functions that we'll be looking to take the derivative of. Now, a couple of notes. If f is to be differentiable at x equals 0, then n must be a number greater than x to the n minus 1 to be defined on the interval containing 0. Okay? And the power rule also includes when n is 1. When n is 1, I have x to the first, so the rule would be bring the 1 out in front, x to the 1 minus 1, so that'd be 1 times x to the 0, which is 1, which is 1. So the derivative with respect to x of just x is equal to 1. Okay, it's the coefficient in front of the term because the degree is 1. Now, I'm going to find the derivative using the power rule for these three functions. So I'm going to raise this up a little bit so you can see it easier. F prime of x, I have x to the 8th, so if I use the power rule, this would be 8 times x to the minus 1, which is 8x to the 7th. Now notice here that I'm using the function notation when I'm working with the derivative. I'm using regular notation when I have the original function. Okay, don't just write equals and take the derivative, because then you're saying x to the 8th equals 8x to the 7th, which isn't necessarily true. Second thing, when you have an expression involving a radical, rewrite it using a rational exponent. So this is going to be x to the 1/4. Now I haven't taken the derivative, so that's why I didn't call it g prime. But now I'm going to take the derivative. G prime of x is 1/4 x to the 1/4 minus 1, which is negative 3/4. So this is 1/4 x to the negative 3/4. Now I'm not crazy about negative exponents. I don't mind a radical in the denominator, but I don't like a negative exponent. So I'm going to write this as 1 over 4x to the positive 3/4. The 4 is in the bottom because of the fraction, and x to the negative 3/4 is x to the positive 3/4 in the denominator. And this is how I would leave my answer. Now, if you left your answer like this, it's not necessarily wrong. You probably won't match an answer in the back of the book because they typically don't like to leave answers with negative exponents. Speaking of negative exponents, I'm going to write 1 over x to the 5th as x to the negative 5. That tells me here then the derivative h prime of x would be negative 5x to the negative 5 minus 1. Now, on the first three examples, I've gone ahead and put a step in where I'm showing you the -1. I don't expect you to do that every time. If it helps, that's fine. But I figure you can probably subtract 1 from a number. So this becomes -5x to the -6, which I'm going to write as -5 over x to the 6th. Okay. And now an application problem, find the equation of the tangent line to the graph of f of x equals x to the third when x is -2, when x is 0, and when x is 1. Well, let's find the derivative first. F prime of x would be 3x to the 3 minus 1 to the second power. This tells me that the slope when x equals -2 is f prime of -2, which is 3 times -2 squared, which is going to be 12. And the slope when x equals 0, I think I wrote an if here, is f prime of 0, which is 3 times 0 squared, which is 0, horizontal. And then the slope when x is +1 is f prime of 1, which is 3 times 1 squared, which is 3. See, as I mentioned before, the derivative is a slope-finding function. I hope that you see that okay. It allows you to find the slope of the line by plugging in the x value of the point of tangency. So now, look what I have here. When x is -2, my y value is -8. Plug -2 in. And my equation of my tangent line is y plus 8 equals my slope, which was 12, times x minus a -2, or x plus 2. There it is. You can put it in slope-intercept form if you choose to. When I plug 0 in at x equals 0, I have the point 0, 0, which means that I'm going to have y minus 0 equals 0 times x minus 0. Well, I'm not going to leave my answer like that. That's just y equals 0. That's the x-axis. And then down here, when x is 3, I have the point 327. So I would have y minus 27 equals, now, let's see, no, I messed that up. I'm looking at the wrong number here. When x is 1, my y is 1 cubed. So I'm going to have, oops, almost messed that one up really badly. I'm going to have y minus 1 equals my slope, which is 3, times the quantity x minus 1. And that would be the equation of the line. Or again, you could put it into slope-intercept form. So those two rules, the constant rule and the power rule, very important, especially the power rule, because we deal with so many polynomials. Now, to help us to get to a polynomial, we need some more rules. So that's what this section is on, this part is on. First off, the constant multiple rule. If you multiply by constant. If f is a differentiable function and c is a real number, then c times f is also differentiable, and the derivative of c times f of x is c times the derivative of f of x. So you just multiply the constant times the derivative. Now this, along with the power rule, allows you to find the derivatives of monomials, or expressions that can be written as a constant times your variable raised to a power, like this one. This is the same as 7x to the -2. So if I want to find y prime, the 7 is multiplied times the derivative of x to the -2, which we were just doing. That would be -2x to the -3. So I would have -14x to the -3, or better yet, -14 over x cubed. See how that works out nicely? That would have taken you quite a while using the definition. Now this next guy, I'm going to rewrite him as 3/7 x to the 4th. Can you see that all right? Hopefully I don't slant the paper too badly for you. So now to find f prime of x, this is going to be 3/7 times, now the derivative of x to the 4th is 4x to the 3rd. So this gives me 12/7 x to the 3rd. Now, I'm hoping that the first two examples may have you thinking, well, do I have to write it like this, or can I just go ahead and multiply that constant that's in front times the n that I bring in front, the exponent that I bring in front in one step, so kind of go jump to here? Absolutely you can. But if you're not comfortable with that yet, don't do it. Keep practicing. So this is 2x to the 1/3. The derivative, y prime, would be, now by the way, I'm kind of going over here to the side. I'm kind of writing it out horizontally because I didn't leave a lot of room below. And so I would like for you to kind of do your work more vertically than horizontally. So I would like for you to go, like for example, you could write this out and then have this step down below and then have this step down below and so on. I think it's just easier that way. It's easier for me to understand at least. So I get y prime, I'll do it on these ones if I can here. Y prime is equal to, I bring the 1/3 out in front and the constant 2 is there, so that's going to be 2/3 x to the, now 1/3 minus 1 is negative 2/3, and I'm going to write this as 2 all over 3x to the 2/3, and that's my derivative. Okay, now showing you the more vertical approach. G prime of x, we'll just get it below here. I'm going to first have to rewrite this. This is 1/4 x, that's the 3/5 power, and it's in the denominator, so that's going to be negative 3/5. So now if I use my power rule and my constant multiple rule, I bring the negative 3/5 out in front. It's going to be times the 1/4. That's going to be negative 3/20. And then I subtract 1 from the exponent. Negative 3/5 minus 1 is negative 8/5. And I would write this. And again, I didn't give myself very much space here. That's why I'm not showing as many of these vertically. But this would be negative 3 all over 20x to the 8/5. Kind of awkward looking. This guy here, before I even start to try to figure out the derivative, I'm going to go ahead and cube the denominator. This is going to be 7 over 8x to the 3rd, which is 7/8 x to the negative 3. Now I'm going to find the derivative. So I bring the negative 3 out in front times the constant. That would be negative 21/8 x to subtract 1 to the negative 4, which I could write as y prime equals negative 21 all over 8 x to the 4th. Okay, again, you can kind of see I'm squeezing it in. I probably should have just left more room so you could see how I like to put the steps vertically when you're taking a derivative. This guy here, I'm going to rewrite him a lot. I'm going to write him as 7 times the quantity 2x to the positive 4, which is 7 times 16x to the 4th, which is, let's see, what, 112x to the 4th? 7 times 16. So now look how simple the derivative is going to be. Bring the 4 out in front. That's going to be 448x to the subtract 1, 3rd power, and it doesn't simplify it. That's how I'm going to leave my answer. So on these problems, you'll see how I took a step or two to rewrite it as a constant times the variable to a power, and then I took the derivative. Now, if you have a sum of differentiable functions or a difference of differentiable functions, as it turns out, this theorem states that it is also differentiable, and it's equal to the sum or the difference of the derivatives. So the derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. Okay? And we can combine this guy with the constant multiple and the power rule with sums and differences of expressions like this, and we can bring in how to take the derivatives of polynomials. So that's what we're going to look at next. Here we go. All right, here's a polynomial. We have f of x equals x to the 4th minus 6x to the 3rd minus 11. I'm going to take the derivative here, and what I'm going to do is I have two differences, so it is the derivative of each one of these terms, and they're being subtracted. So notice the first term, x to the 4th. F prime of x, the derivative of x to the 4th is 4x to the 3rd. Then I have a minus sign, minus, and then I have another little monomial here where I'm using the scalar product and the power rule. So the derivative of 6x to the 3rd, you bring the 3 out in front, subtract 1 from the exponent, and then the minus 11, that's a constant. The derivative of a constant is 0. I'm done. Try again. Here, with b, I'm going to find g prime of x. Now, before I find g prime of x, notice the first term, I'm going to write this as negative 1/4 x to the third plus 8x minus 19. Now I'll do the derivative. So I bring the 3 one term at a time. These are sums. So 3 times the 1/4, negative 1/4 is negative 3/4 x to the second power. The derivative of x is 1. So the scalar times this would be 8 times 1. So this is going to be plus 8. And of course, the minus 19 is a constant. The derivative of minus 19 is 0. And there's my answer. Look at that exponent of 3. Look at that exponent of 4 there. Can you imagine doing this one by definition? All right, this one's another peach. Only I changed my independent variable to t. That's okay. You can have any independent variable you want. I have 4 terms, and I'm going to take the derivative one at a time. I'm going to call this p prime. And this is equal to the derivative of t to the third is 3t to the second. The derivative plus here of 6t squared, you bring the 2 out in front, that's 12t to the first, or just 12t. Minus, minus, the derivative of 5/3 t, well, the derivative of t is just 1, so the derivative of 5/3 t would be just 5/3. And of course, plus 16 is a constant. The derivative of plus 16, or positive 16, is 0. And there's my answer. Okay? And as you can hear in the background, they're doing some work here at school, and going to be interrupted a few times with some extraneous noise there. Sorry about that. Next example. Does the curve y equal x to the fourth minus 2x to the second plus 2 have any horizontal tangents? And if so, where? Well, horizontal tangents means that the slope of the tangent line is 0 because it's horizontal. So what I'm going to do is I'm going to find the derivative, which is 4x to the third, that's the first term, minus 4x, and of course the derivative plus 2 is 0. I'm going to set the derivative, which is my slope finding function there, equal to 0 to see if I have any horizontal tangents. And I'm going to solve this equation just like I did in my algebra days. Factor out of 4x, I get x squared minus 1 equals 0. So I get 4x times the quantity x minus 1 times the quantity x plus 1 equals 0. So I get x equals 0, 1, and negative 1. Well, it looks like I'm going to have 3 horizontal tangents. And it should kind of make sense because typically these kinds of graphs, a quartic like that with a positive lead coefficient, probably looks a little bit like a W. So I have a horizontal tangent, and a horizontal tangent at x equals 0, 1, and negative 1. Now it says, does this curve have any horizontal tangents? Yes. If so, where? I could just state the x values, but I'll go ahead and say at plug 0 in, 0, 2. Plug 1 in, I get 1 minus 2 plus 2 is 1, so at 1, 1. And plug negative 1 in, and I think I'll also get a positive 1. I think I have some symmetry here. Yep. And so I have negative 1, positive 1. Okay. Stated my answer. Now, if in the back of the book on a problem like this that you work and they have just the x values, that's fine as well. I just like to write them as ordered pairs, even though it's a little bit of extra work. Now, we have some key theorems and rules to help us to take the derivatives of constants, of powers, of sums and differences, of constant multiples. And let's not forget about our trig functions. We'll start off with sine and cosine, the most basic ones. Now, these are, again, proven to be true by using the definition. We're not going to go through it. I think it might be in the book, and if it's not in the book, I'm sure you can look it up online. But essentially what it comes down to is for the derivative of sine and the cosine functions, the derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is the negative or the opposite of the sine of x. With that stated, y prime for y equal 9 sine of x would be constant times your function here would be 9 times the cosine of x, because the derivative of sine of x is cosine of x. I'm going to think of this as 1/5 cosine of x, and f prime of x, well, the derivative of the cosine of x is negative sine, so this would be negative 1/5 sine of x, or if you want to, you could write this as negative sine of x over 5. I think this is just as good. And here, notice with the sums and differences, we take it one term at a time here. Y prime, well, the derivative of 2x is the power rule. That'd be 2x to the first, or x squared, that'd be 2x to the first. The derivative of the cosine of x is negative sine x, so minus the sine of x. And the derivative of minus 11 is 0. So we are now able to a little bit more efficiently find the derivatives of some real basic functions. And that comes into play and useful when we're doing any kind of an application problem. So let me try an application problem here with you. Maybe two. Okay. We use the derivatives to not only find the slopes of tangent lines, but we can use them to help us determine the rate of change of one variable with respect to another, which is instantaneous rate of change. Now in algebra, we found constant rate of change, kind of the slope. But since we're able to find the slope at any point on the curve, we can find instantaneous rate of change. Now this is good for, as I've got listed here, population growth, population rates, rates of water flow, velocity, and acceleration. Now let's think about velocity and acceleration, or especially velocity. If we consider the motion of an object moving in a straight line, and they love straight line motion problems, we usually have the line running either horizontally or vertically. If the line is running horizontally that your object is moving along, we consider velocity to the right positive and velocity to the left negative. If it's vertical, we consider velocity going upward as positive and velocity going downward as negative. A position function, right here, which they like to call S, gives the position relative to a starting point, sometimes it's the origin, of an object as a function of time. So you'll see an independent variable of t, S of t. You may remember that from your pre-calculus days. And over a period of time, the change in time, period of time here, the object changes its position by thinking of this as delta s, which would be the difference in the y values of this function or the s values in this function. So it's the second position minus the first position. Average velocity is delta s over delta t. That's our slope. But instantaneous velocity, that's kind of cool too. So I'm going to show an average velocity problem, and then I'm going to work this to an instantaneous velocity problem. So to find the average velocity over a time interval for this function here, let me underline this. A ball is dropped off a building 160 feet tall. Its height s at time t is given by the position function. S of t equals negative 16t squared plus 160. S is in feet, t is in seconds. Find the average velocity. Well, the average velocity is delta s over delta t. So this would be s of 2 minus s of 1 all over 2 minus 1. Now, if I plug 2 into here, s of 2 turns out to be 96. If I plug 1 into here, I get, let's see, I get 144, and that's all over 1. So that's going to give me what? Negative 48 over 1, or just negative 48. And this would be in feet per second. Why is it negative? Because it's dropping downward. As I mentioned, if you're looking at like a vertical line, going upward, velocity is positive. Going downward, velocity is negative. Now, don't say negative 48 feet per second downward, because that's kind of redundant. It's almost like the negative and the downward cancel one another out. You can either say negative 48 feet per second, which is preferred, or you could even get away with 48 feet per second downward. Okay? What's next? Well, let's look at a shorter time interval. Instead of a whole second going by, let's see what's happening to this ball as far as its velocity, its average velocity, in the first half of a second there. Well, actually, after 1 second, it dropping the next half second. So this would be s of 1.5 minus s of 1 all over 1.5 minus 1. Well, s of 1.5 turns out to be 124. S of 1, well, we already know that that's 144. And 1.5 minus 1 is 0.5. So I have negative 20 over 0.5, which is negative 40. Notice it is not going as quickly downward. This is going negative 48, this is going negative 40. It's because gravity hasn't had as much of an overall effect on it. It's been in the air less time. Next, over the interval from 1 second to 1.1 second, s of 1.1 minus s of 1 all over 1.1 minus 1. Well, s of 1.1 is 140.64. S of 1 is still 144. And 1.1 minus 1 is 0.1. You hearing that construction being done, people? So this is negative 3.36 over 0.1, which is negative 33.6, and this would be in feet per second. Again, it's not going quite as quickly as the last one as the one before because it hasn't had as much of an effect on gravity, the acceleration pulling it downward. Now, what I'm trying to get you here is to show you that as the difference in the time gets smaller, my average velocities, and that's what I'm doing here, my average velocity is going to approach the instantaneous velocity. So let me kind of finish this problem here in some ways by first talking about instantaneous velocity. To find the instantaneous velocity, when we look at the average velocity as delta t goes to 0, is the difference in time for the average velocity. This is my average velocity. This is my difference quotient expression. We let delta t go to 0, and we get what we call s prime of t, our function, which is velocity, instantaneous velocity. So back here, if I take s prime of t, which I just said was my velocity function, v of t, I would get negative 32t. If I substitute the velocity at or define the velocity at time t equal 1 second, v of 1 would be negative 32 times 1, which is negative 32 feet per second. Notice here in the three time intervals that I did, if I can find my paper, how it was approaching negative 32. Went from negative 48 to negative 40 to negative 33.6, that's pretty close, to the instantaneous velocity at 1 second, which is negative 32 feet per second. So this is a way to find instantaneous velocity. Now, sometimes students ask me, what's the difference between velocity and speed? Aren't they the same thing? Well, we define speed of an object as the absolute value of the velocity. So it doesn't matter if it's upward or downward, the speed's going to be positive. And this guy you definitely should remember, if not from pre-calculus, perhaps from your physics class. It is the position of a free-falling object that neglects air resistance. Under the influence of gravity, our function s of t is equal to 1/2 gt squared plus v sub 0 t plus s sub 0, where g is gravity, either negative 32 feet per second squared or negative 9.8 meters per second squared. V sub 0 is the initial velocity. Your subscript is 0. That means when t is 0. So the initial velocity, so like if you just drop an object, the initial velocity would be 0. And s sub 0 is the initial height or the position. So let's try an example here where we're going to try to find perhaps an instantaneous velocity. A ball is thrown straight downward from the top of a 220-foot tall building with an initial velocity of 22 feet per second. What's the velocity? Okay, after 3 seconds. So I'm going to go to this guy here, and because this is in feet, I'm going to use negative 32. Goes right in there, so 1/2 times negative 32 gives me s of t is equal to negative 16t squared. V sub 0 is not 0 because they throw it downward. It's initial velocity of 22 feet per second, but it's going downward, so minus 22t. And s sub 0 is the initial position or the initial height, which in this case was a 220-foot building. So to find the velocity, I take the derivative. That's negative 32t minus 22. And to find it after 3 seconds, I find v of 3, which would be negative 32 times 3 minus 22, which is negative 96 minus 22, which is what? Negative 118. So the velocity of the ball 3 seconds after being thrown is negative 118 feet per second. So that's the exact initial or the exact velocity, the instantaneous velocity of this. What is the velocity after falling 108 feet? Now this didn't give me a time like it did back here. Here it was easy. I have the derivative, right there it is. I just plug in the number. Well, I don't have the number for time. I don't have the number for time. But I do know that it dropped 108 feet. Now it started out 220 feet off the ground. So if it drops 108 feet, that means it is 112 feet off the ground. So that would be my position or my height. So what I'm going to do is I'm going to go to this guy right here and I'm going to plug this in for my position. I'm going to write 112 equals negative 16t squared minus 22t plus 220. I'm going to bring everything over to the left side because it's quadratic. I get 16t squared plus 22t minus 108. And that equals 0. I can divide through by 2. Yep. So I get 8t squared plus 11t. Let me raise this up and straighten it out there for you. Minus 54 equals 0. I got to get an odd one in the middle, so I'm thinking it's 8t and t. Not 8t and t, 8t and t. And probably 9 and 6. 3 and 18. I gotta get. Let's see. I'm pretty sure this one works. Let's see, 9, 6. That's no good. 2 and 27. There we go. So the 2 goes here. The 27 goes here. Whew. And let's see. I got to get a plus 11. So plus here, minus here. Well, this is going to give me a value that's negative, so that's not much help, but this is going to give me t equals 2. So 2 seconds after the object has been released, it has already fell 108 feet, so we just want its velocity then, so I'm going to find v of 2. So this would be, going back to my v here, right, that would be negative 32 times 2 minus 22. So that's negative 64 minus 22 is negative 86. So the velocity of the ball is negative 86 feet per second after the instant, let's say, it has fell. It has fallen. It has fallen. I don't know. We'll go with it has fallen 108 feet. And there's my answer. You may notice here with the application problem, I'm trying to stress here, write your answer out in a short sentence. Of course, use proper English if at all possible and be legible. And we're often running with derivatives. Now we have more derivative rules. We know derivatives for sums and for differences and for power rule and constants and such, but we still have to consider what's going on if we have functions that are products or quotients or maybe even composite functions. Now getting back to this problem, I was trying to think of a building, how many floors this building would be if it's 220 feet tall. I figured about 10 feet to a floor, so that would be 22 floors, which I think I remember a building here in town that was 22 floors. It used to be 23, but that's another story.